Hey everyone, greetings to Dr. Yan, our lecturer, and to all of my friends watching this video. Welcome to the video presentation of our V2 steam engine mini project, in which the syringes serve as the cylinder of a genuine V2 engine.
So we are from Group 2 and I am Darren Manuel. So along with my group members, which are Anderson, Jack, Marshall and Omero. So our project for Group 2 is the steam engine V2. For the introduction of our project, so the understanding of heat, temperature and energy took nearly 250 years to develop, leading to the formulation of the first law of thermodynamics. Heat engines, which convert heat energy into mechanical work, follow a cycle where heat is extracted from a source. Work is performed and any remaining heat is discharged into a cooler reservoir. A steam engine, which is a small-scale demonstration of a heat engine that utilizes the expansion of steam to generate mechanical work. This is to understand the principles of thermodynamics and energy conversion.
Okay, moving on to the description. First, a V2 engine, also referred to as a V2 engine, is a form of internal combustion engine in which the cylinders are typically arranged in a V shape with a 90-degree angle between them. When viewed from the front or rear of the engine, the cylinders form a V shape if you look at it in real life. But in our case, however, we line it with its own, meaning that it is lined parallel to each other. This is because initially we intended to construct a 4-cylinder engine because 4-cylinder engines are typically configured either inline or boxer. Due to sealing and steam filtration issues, safety concerns, and the frame's unsteadiness, it was unable to be constructed. We changed it from a 4-cylinder steam engine into a V2 syringe-based steam engine. As you can see in the video, we waited until we could observe a very slight movement of the crankshaft. Once it starts to go up and down, we rotate it. The decision to construct a V2 syringe-based engine originated from the fact that fewer syringes used meant fewer movable parts and components to fabricate and assemble, thereby reducing the complexity. Secondly, constructing a steam engine with syringes as cylinders does not require the same level of precision as manufacturing a 4-cylinder engine. While it is still essential to establish a good seal between the syringe and piston, the tolerance requirements are typically less rigorous. So therefore, in general, the V2 configuration provided a more feasible and manageable solution for our project, which is a 2 syringes based steam engine. So now moving on to the methodology part. The materials used are carefully chosen and we made sure that they are 100% household materials in accordance with the needs of this project to ensure that the project functions properly. So the materials used for this project are cardboard, round cardboard, plywood, LDPE and plastic tubings, oil stainless steel container, motorcycle chain, 2 syringes 10 milliliters, zip tie, Vaseline, cooking oil, iron rod, epoxy, screws, tube connector, and IO wire. The following are the methodology of the project. So firstly, we used a grinder to remove the motorcycle chain. Then we rolled a metal wire around the metal rod and welded them together to create a strong structure capable of rotational motion. This assembly is also known as crankshaft of the syringe-based steam engine. Then we cut 3 plywood pieces measuring 20 cm times 5 cm, and this will serve as the base and frame of the syringe setup. The dimensions are crucial to ensure that the pistons are not too far apart. We drilled small holes on the sides of the structure and inserted the metal rod through them, also known as the crankshaft. For the base of the syringes, we drilled holes with a diameter of 1.5 cm, matching the size of the syringes to ensure a proper fit and it doesn't move left or right. After cutting the plywood pieces, we screwed them onto a round piece of cardboard which will serve as the base of the structure, and using zip ties, we attached them to the sides of the syringe base for added stability. We also cut a cardboard circle and attach it to the ends of the crankshaft, and this will assist in the movement of the crankshaft. Third, we cut LDPE tubes with a length of 97.5 cm. This is important to note that longer tubes can result in pressure loss in the steam system. Next, for the syringes, we cut half of the rubber portion on the top part of the piston. This is done to reduce friction between the rubber and the inner surface of the cylinder. And then we inserted the syringes through the previously drilled holes and applied clear epoxy on the outer surface of the syringes. This is to prevent unnecessary movement during the rotational motion of the crankshaft. A small hole was poked on the outer surface of the cylinder to allow it to move up and down. Then we applied cooking oil in the syringe, and this functions as lubrication to lessen the friction that the syringe's piston experiences. If it's not working, we used Vaseline as an alternative. Then we connected the LDPE tubes into two sections, measuring 16.5 cm each. One end was attached to the tube connector and the other end was connected to the tip of the syringe. Then, next, we applied epoxy to ensure a secure connection and prevent any pressure leakage. We used a stainless steel oil container and welded the inner diameter of the opening of the oil container. We also applied epoxy on the outer surface of the container to ensure that no pressure would escape. We drilled a hole on the top of the container and inserted a steel straw to allow the steam to escape. Lastly, we filled water into the oil container through the steel straw. Next, we connected the 97.5 cm LDPE tube to the steel straw and the tube connector. Then we heated the oil container and waited for the water inside to boil. Once the water boils, steam will be transferred to the syringes, and this will determine if the syringes will move up and down. But according to the outcomes of our project, it seems that the pressure has been transferred successfully without no pressure leakage around the oil container.
In this slide, we have the data obtained for this mini project. So for mass of empty pot, we have 200 grams. Initial mass of water, we have 286 grams. To get initial mass of water, we firstly take the mass of water and pot minus the mass of empty pot. Next, we have final mass of water, which is 276 grams. And time taken for steam engine left running is 30 seconds. Latent heat of vaporization for water is 22.6 times 10 to the power of 5 JkG. And number of revolutions made by this in that 30 seconds is 18 revolutions. And finally, the distance push of syringes piston in one direction is 5 cm. Next, to calculate the efficiency, first we need to calculate the heat supplied by the heat source. So to calculate the heat supplied, we have the formula, which is heat in equals to delta M times L over time. Delta M is the change in mass of water, which is 0.01 kg. L is latent heat of vaporization for water, which is 22.6 times 10 to the power of 5 JkG, and T is 30 seconds. Latent heat of vaporization of water is defined as the amount of heat energy needed to evaporate 1 kg of water at boiling point. So using this formula, we get heat supplied equals to 75 joules. Next, we have to calculate the work done by the syringe to push the piston. So the formula for work done is work done equals to force times 2 times the distance times the number of revolutions, which is N. So for force, we have the mass times the gravitational pull of the Earth, which is 0.01 times 9.81. Then we times 2 times 0.07, which is the distance pushed by syringe in one direction, and times 18, which is the number of revolutions. Then we get work done equals to 0.124 J. Why we need to times 2 for the distance? Because when the engine is running, the syringe's motion is up and down, so it travels twice. And lastly, to calculate the efficiency, we have the formula work done over heat supplied times 100%. So for work done, we have 0.124 joules, and heat supplied equals to 75 joules. 0.124 joules over 75 joules times 100%, we have 0.17% of efficiency. The work done is very low compared to heat supplied because some of the steam leak out from the syringes. The heat energy from the steam also escape to the surrounding when traveling from the pot to the syringe through the tube.
Hi, I'm Jacqueline Pauline. I'd like to discuss about the outcomes of our V2 steam engine mini project and the factors that resulted to its low efficiency. In addition, I'll discuss the several modifications that might increase the engine's performance and manage some of the difficulties we faced during the project. Let's start by discussing the results. We calculated the work done by the steam engine was 0.124 joule, while the heat supplied was 75 joule. Based on these values, we determined the efficiency of the V2 steam engine was 0.17%. This low efficiency is due to energy losses caused by the excessive heat supplied to the system. When the heat exceeds the engine's capacity, it results in energy dissipation through sounds, vibration, and light energy. These losses contribute to the overall inefficiency of the engine. To improve the efficiency of the steam engine, we implemented several steps during the project. Firstly, we choose a portable stove as a heat source because it provides a consistent and controllable heat output as compared to alcohol burners or tea light candles. This ensures a more stable and efficient operations. Secondly, we applied an appropriate amount of lubricant. In this project, we use Vaseline to the syringe to reduce friction and improve the piston movement within the syringe. This minimizes the energy losses caused by the friction, resulting in smoother operation and increased efficiency. Lastly, we carefully seal any gaps or leak between the syringe by applying the appropriate amount of glue. This prevented steam from escaping and allowed for more efficient pressure build-up. These steps significantly enhance the overall efficiency and performance of the steam engine, making it more effective and reliable system. However, there is still room for further improvements. Now let's discuss some modifications that can be implemented to enhance the efficiency of V2 steam engine. Firstly, use a proper lubrication such as high temperature lubricant to ensure smooth operation of the syringe. Secondly, add a condenser to convert steam back into the water to reuse back the water and reduce the water loss during the operation. Lastly, use a pressure vessel such as a spray can to increase the pressure. During the project, we faced difficulties such as achieving a proper seal between the syringe piston, which led to steam leakage and reduced efficiency. Secondly, heat management was challenging due to limited resources, causing heat losses and overheating problems. The durability and limitation of household material use also affected the efficiency of the engine. Additionally, building a working steam engine, even though it's just a mini project, it requires significant effort, persistence, and time because it is involving trials and errors. To overcome these challenges, we recommend conducting a true leak test to ensure the proper seal. Moreover, monitoring and monitoring the heat resource and adjusting it as needed helps maintain the desired steam production temperature to improve the efficiency. Whenever possible, Try to use higher quality or specialized components such as heat-resistant tubing. Finally, setting realistic expectations, setting time, breaking down tasks, and embracing the learning process will, will ease the progress and helps to improve skill. By implementing these modifications and addressing project difficulties, um, we can improve the efficiency and performance of the V2 steam engine to make it more reliable and effective system.
Next, I'll be talking about the significant impact of the mini project with relations to the course outcome and mechanical program outcome. As a result of the implementation of this mini project, it has posed a significant impact on the student, particularly in regards to the second course learning outcome and the third program outcome, which are the ability to analyze and solve engineering problems related to heat engine cycle and the ability to investigate the problem and provide options to solve steam power cycle system application. Both of these are referred to as the ability to analyze and solve engineering problems. While we were working on the design of the V2 steam engine, we ran into a number of issues that stopped us from reaching our objectives. The analysis skills that we have developed thanks to this project have been invaluable in resolving the challenges we faced along the way and ensuring the project's success. Aside from that, the completion of this project has made it easier for us to study issues and suggest potential solutions to difficulties with steam engine cycles. Next are the safety precautions. So, constructing a thermodynamics project involving steam-powered systems requires careful adherence to safety precautions to mitigate the risks involved. Failure to address this risk adequately can result in accidents or injuries. So first and foremost, it is essential to ensure proper design and engineering of the system. This includes considering factors such as pressure and temperature limits, material selection, and the structural integrity of the components. The pressure within the pot supplying steam to the syringe should always be aware of. Excessive pressure could cause the pot to explode and cause injury. Understanding the safe operation of the equipment, emergency procedures, and proper use of personal protection equipment are critical aspects of safety in thermodynamics projects. Wearing protective equipment such as safety goggles and heat-resistant gloves to protect one's eyes and hands from potential hazards. Adequate ventilation and fire protection systems should also be in place to prevent the ignition of flammable materials. Lastly, be aware of hot surfaces both during and after using the V2 steam engine. And lastly, allow adequate cooling time before touching any hot components or surfaces.
So in conclusion, the steam engine is a small-scale demonstration of a heat engine that utilizes the expansion of steam to generate mechanical work. The work done by the prototype is 0.124 joules. Because the heat supplied is 75 joules, therefore, the efficiency of the steam engine, which is calculated by dividing 0.124 by 75, is 0.17%. So, the reason why it is decreased in efficiency is caused by the excessive heat supplied. So the solution to our problem is that we could have looped the syringe more so that it will stop friction. Next, we can use a portable stove to supply ample heat and just the right amount required for our project. And lastly is to seal any gaps from the syringe. It can be the nozzles or the gaps between the pistons itself.